Thanks for the introduction. Today I'm going to talk about our work, Qtenon, towards low-latency architecture integration for accelerating hybrid quantum classical computing. This work is supervised by Professor Jianwei and Liqiang. So first, I will give some background information about our work. First is the hybrid quantum classical computing. This is a really promising way to take advantage of both the quantum and classical computers. On this slide, I'm showing the most popular type of hybrid algorithm called VQA. Here is how it works. In each iteration, we will run a parameterized quantum circuit and measure the results. This result is then optimized by the classical computer and update the circuit parameter for the next run. This loop will continue until the cost function stops improving. So on this slide, I've shown some examples of the hybrid algorithms. For example, the VQE, QAOA, and HiQ set. They require computation from both the quantum and classical part. Now, let's take a look at how today's quantum systems are typically designed. On the hardware side, most systems follow a decoupled architecture, which usually consists of 3 parts and 2 connection interfaces. The host, which will compute the circuit and the parameters, and it will pass the compute program into the FPGA controller, which will then translate high-level quantum programs into low-level pulse instructions and manage the communication between the quantum chip. And the quantum chip will execute the actual quantum circuit. On the software side, in addition to traditional ISA executed on CPU, the system need to define a dedicated quantum ISA for the quantum part. And these instructions need to be transferred back and forth between the quantum and the CPU part. So now we started by profiling the runtime of the current system when running those hybrid quantum algorithms. And we find that over 19% time are classical operations. And the classical time percentage will increase with the number of qubits. And among those classical components, the host computation will take up most of the time. So based on this profiling result, we have identified 2 major limitations in current quantum system design. To explain this, we have compared our work with the decoupled system EQASM and ISCA'25. So the first limitation is the communication bottleneck between the quantum system and the host. Both EQASM and ISCA'25 lack dedicated support for the communication between the controller and the CPU and rely on general purpose interfaces like USB and Ethernet, which will introduce latency in order of milliseconds. The second limitation lies in inefficient communication between the quantum and the host. So because of those separate memory architecture, this execution will be strictly sequential. And this also leads to high recompilation overhead, as the quantum program must be regenerated in every iteration, which also introducing latency in milliseconds. So this constitutes the need for a tightly coupled system. So next, I will explain the challenges when building this tightly coupled system. The first challenge being how to design a unified memory system and how should we put the quantum memory space. And specifically, we need to define the memory structure within the quantum controller and also enable fast interactions between the host and the controller. The second challenge being how to design the quantum controller. So it needs to be high performance while meeting the demand for key requirements. First, it should support enough bandwidth between the controller and the quantum chip. Second, its interface with the host must support efficient interactions. The third challenge being the ISA design. So we need to define a unified instruction set that works for both the host and the quantum accelerator. And this should support efficient computation and data communication between those two. We'll also maintain the memory consistency between the controller and the host part. So we will introduce our work Qtenon, which consists of two parts, the hardware part and the software part. For hardware part, we have designed a unified memory interface with the quantum controller and the compute unit. For the unified memory, we have positioned the quantum controller cache at the same level as the L1 and L2 cache and design dedicated data paths to enable fast communication between those two. And for the quantum controller cache, we organize it as a 2D memory space. And for the first dimension, we have partitioned it into 5 segments. And on the second dimension, those segments, within each segment, there is a list of cubic chunks. This 2D organization makes the system easy to scale. Next, we have partitioned this quantum cache into 2 parts. For the private part, we have the pulse segment, which will store the control pulses for the quantum chip, and the SLT part, which is used for optimization, and I will explain it later. And for the public part, those are the program and register file with measurement. All those are accessible to users. And for the quantum controller design, we have designed 4 dedicated data paths between the host and the quantum controller. The first data path between the host is between the host register and the public quantum controller cache. It uses the ROCC interface and can transmit 64-bit data per time with just 1 cycle latency. And the second and the third data paths connect host L2 cache with the quantum controller cache. One is dedicated to public data transmission with other dedicated to private data transmission. These connections use a dedicated quantum controller interface and this interface helps to bridge the discrepancy between 2 memory systems. This setup enables large data transmission with low latency. This is the design of our quantum controller cache interface. So when designing this cache interface, we have faced 3 design challenges. The first challenge was how to maintain the memory consistency between the quantum controller and the host. To address this, we use a hardware-software co-design approach. On the hardware side, we have introduced a memory barrier that ensures the updated data is properly stored, and the software solution will be discussed later. And the second and the third challenge was how to handling out-of-order responses and dealing with varying data wise. This was solved using our custom designed reorder buffer key and write buffer key. You can find the detail in the paper. And for the connection between the quantum controller cache and the quantum chip, we follow in the existing hardware protocol and use ADI interfaces to establish the connection. And for the post-generation part, we have designed a 4-stage hardware pipeline to maximize parallelism and eliminate redundant computation. And the detailed procedure can also be found in paper. So in first stage, we will load the data from the program index buffer. And stage 2, we will parse the instructions and use SLT to determine whether the corresponding pulse has been generated. If not, we will start computation in stage 3. And on stage 4, we will store the generated pulse for the connection. And next, we will explain the detail of our SLT workload. So this SLT table is used to index pulse data based on the gate parameters. It works similarly to the cache tag management in classical computer. The gate parameter is stored and used as a key to index into SLT. If the current gate parameter matches the tag, the system will simply increment the counter and returns the corresponding queue address. If not, it will use a least count replacement policy and fetch the data from the memory and use this data to update the SLT table. So on the software side, I will introduce our proposed ISA design and how we can keep memory consistency. So we have designed our ISA based on the extending ROCC interface. These extended instructions can be divided into two main categories, the data communication and computation. For the data communication, each instruction corresponds to a specific data path, and we introduce the concept of queue address, which will index the qubit into the address. And in our ISA, every quantum gate is treated as a parameter, so they can be updated using either queue update or queue set. This design enables dynamic incremental compilation for the quantum part. And for the memory consistency, the simplest approach is to use a fence instruction, which will synchronize the data between the quantum controller and the host. However, using this fence instruction will enforce a ordering between the memory operations. So in our case, this means the classical part has to wait until all quantum operations are finished before continuing to compute. And this will introduce long waiting time on the host side, which will significantly reduce our system's efficiency. So to reduce this long waiting time, we propose a memory barrier with fine-grained synchronization. On the quantum set, our memory barrier will provide detailed tracking of which part of operation has been synchronized, and the hardware design is shown before. And on the host side, the system can simply query the status of a specific address. So this is done through the ROCC interface and introduce only one cycle latency. So if part of the data is already synchronized, the host can proceed immediately without waiting for all quantum operations to finish. Next, we will show our evaluation result. So the Qtenon is designed as an ASIC chip, and it's built on top of ChipYard project. So the classical part, we use open source RISC-V core like the Rocket core and Boom core, and use our Chisel language to develop the quantum controller. And all the results are simulated using the FireSim framework. So our benchmark consists of 3 main VQA algorithms and with different qubit numbers. And our baseline comparison is a decoupled system with 100 gigabytes internet connection. And here is the Qtenon's floor plan and the hardware configuration. So the overall performance comparison is shown in this figure, and we achieve about 300 times optimization on the classical side and about 15 times on the end-to-end result. And we show an example time breakdown of our system performance. And we can see we have increased the quantum percentage from only 8% to 19%, and reduced the end-to-end time from 200 milliseconds to 20 milliseconds. And other detailed performance analysis can be found in our paper. Okay, that's all. Thanks for listening, and I'm happy to take any questions.